everyone. Today we are very happy to have Daniel to tell us what he has been working on star formation. So although we already know Daniel for a few years, that will give you a brief introduction of his background. He got his PhD from UCLA in 2008, and after that he went, the PhD, the bachelor degree in 2008, and after that he went to Leiden Observatory, did his PhD, and then got a degree in 2014. After that he moved to Heidelberg as a first postdoc term until 2016. And after that he moved to Leiden Observatory to join our node. And also an astrochemistry group there until 2019. Then he joined us afterwards as an ASIAA fellow, starting from 2019. So today, we are happy to have him to tell us about his work. Let's welcome him.
So yeah, thank you all for coming. Thanks to the organizers for giving me this opportunity to present my work and introduce what I have been doing in the past few years. So it is also a privilege to actually be here instead of being online, so I'll try not to waste that. This slide shows a brief background of my profile. So as Tantan said, I graduated from UCLA with my bachelor degree in astrophysics and mathematics. So I focus on combinatorics and numerical analysis in mathematics. Then I moved to the Netherlands to do my graduate studies at the Leiden Observatory. So at the bottom there is a brief overview of what I've done in the past few years and also the highlights. So let's get started. The main motivation of my research is to understand how do we all actually get to here. It is in these dark molecular clouds that we can try to understand how planets form and also the origin of our own solar system.
Sorry, people complain about the audio seems not good. So maybe you switch on yours, mute, and I stop.
Okay, that's fine. Is that
okay?
Is that okay? Okay. Yeah. So it is in this dark molecular clouds that we can try to study in detail how stars and planets form, and to answer whether or not the solar system is common. Through the observations of molecular lines, we can try to understand and answer the question whether life can emerge in this other planetary systems other than our own. The main focus of my research is actually the last question, is how do we actually test our theories? We know there are very many models of how stars and planets form, but the tools how to connect the theory with observations at various wavelengths are still lacking. And furthermore, how to actually test those theoretical models. So the cartoons depicted here are showing the stages that the low mass stars form and also their planetary system. It starts with the collapse of the dense core, where a disk will eventually form. And this disk will eventually evolve to what we know of today as protoplanetary disks. And this disk will form the planetary system. These four stages describe how the mass is transferred from the large scale, where the density is very low, to the center, where the density is high, and that is where the stars and planets form. The different stages are not to be confused with classes. So stages mostly describe the masses. So So that is what you can connect with theoretical models. While classification, that's based on classes, are based on observations. So they do not necessarily correspond to the theoretical models one-to-one. The end product of this process is, of course, our own solar system. It has rocky planets in the inner parts and gas giants in the outer parts. The solar system bodies, including the asteroids and comets, are actually relics of the star and planet formation process. All of these bodies went through all the stages that were described in the previous slide. Now, in order to understand how the star and planet formation process actually formed these planetary systems, we can also look at the exoplanet population. Here I plot the exoplanet mass as normalized to the host mass as a function of their semi-major axis. Each of the symbol corresponds to the size of each of the exoplanets. So you see there are some rocky planets, very small, close to the host star, and also very large gas giants. And the corresponding size to the Earth for some of those smaller planets are shown in the inset. As you can see, they're actually very diverse. And then we can also overplot our own solar system planets that occupies different space of this diagram. So none of the exoplanets are actually similar to our own solar system so far. What ALMA in the submillimeter has done actually has shown us a great detail of the birthplaces of these planets. So these are all the protoplanetary disks that we observe toward the Taurus molecular cloud. So they're all similar in ages. They are showing a huge diversity in terms of sizes and also the architecture, the structures. So some has rings and gaps, and some actually very tiny and smooth. So it could well be that the diversity of the exoplanets are actually inherited from this diversity in the structure of the protoplanetary disk. It is known that these gaps could be corresponding to planets. So this is what the numerical study shows, that gaps are linked to protoplanets. Now if we can convert those gaps or spirals into protoplanets, they all populate here. So they're all actually different from the known exoplanets that we know today. The main reasons why they're different, it could be that these disks are young. So if we actually do the migration calculations, all these protoplanets can actually evolve to the known exoplanets today. But then how those processes are actually affecting the chemical history of those planets and whether or not those actually will resemble our own solar system is still to be determined. One way, the location of these gaps and planets also affects the chemical history of that disk. The comets or the relics of the star and planet formation can be measured in terms of their composition. So this is CO with respect to HEN for the different comets in our solar system, and also the interstellar comet 2I Borisov. So most of the comets are actually between 1 to 100 in terms of their CO over HEN ratio. Their CO and HEN ratio reflects on their location where they were born, while the two interstellar comets are actually slightly different than our own solar system comets. So the question then, what are the physical processes that shapes and affects all these different protoplanetary disks, and how will that actually change the chemical composition of the comets and asteroids to study our own, to understand our own solar system formation, and also what's happening in other planetary systems. So this talk is split into 3 sections. The first section, I will go into the solar system bodies as a laboratory for the physics of star formation. The second, I will go into the disks and the accretion process. And finally, I'll end what the dust and the gas composition actually tell us about the star and planet formation. So the solar system contains relics of the star and planet formation. So what do they actually tell us in terms of these small millimeter and centimeter dust grains? In order to study the solar system, we actually have to utilize the full periodic table. In astrochemistry, we just care about hydrogen, helium, carbon, nitrogen, oxygen. But to really understand the solar system history, we actually need almost the complete periodic table. Most of the things that I'm going to talk about in the next few slides rely mostly on the sodium and magnesium here, and iron, and also some of the elements that are here on the right side. In particular, carbonaceous chondrites that actually contains chondrules are actually formed in the distant past when our own solar system was formed. So carbonaceous chondrites are the earliest remnants of the star and planet formation process. If you look at the chondrules in details under a microscope, you see all these glassy textures, glassy dust grains, and they're all crystallized. The different colors correspond to the different mineralogy. So they all contain different minerals. The reason why they're glassy textures like this is that they were heated in the distant past up to temperatures of above 2000 Kelvin, and then it forms the dust grain again very quickly, and then it forms the glassy texture here. So this process is shown here. So the dust grain heated to 2000 Kelvin or so, and then it cools very rapidly within minutes, and it has to happen when the disk actually contains gas. So that's had to happen within 2 million years. The most important thing is that they contain sodium, potassium, and sulfur, which are so-called volatiles. So these elements escape to the vacuum very quickly, so you actually have to cool this process between minutes to hours. If the cooling process is shorter than minutes, then the dust grains do not crystallize. If it's longer, also it doesn't actually produce these structures. So this limits us into what kind of physical processes that can actually happen in this disk to form these glassy small grains. In particular, chondrules and CAIs, so-called the calcium aluminum inclusions, are actually one of the first dust grains that are formed in the early solar systems. So you can age this different parts of the grains to indicate that actually CAIs form first, and then chondrules actually form throughout the age of the disk evolution. So from 0 up to about 3 million years. Recently, it's shown that some of the chondrules actually form at the same time as CAIs. So all this meteoritic evidence actually shows us the physical conditions of the early stages of star formation, as hinted from our own solar system bodies. Then these grains are actually present at the same time that a disk around our young sun was actually forming. So these processes are actually occurring during the disk formation process. One way to produce chondrules is through impact splash. So pretty much you have multiple planetesimals or rocky bodies like the moon or similar to various moons in the solar system, and you collide them. So this is collisions is also a way to actually form our own moon. We can use this simple toy model of expanding splash of dust grains and evaporate dust grains, and we can calculate how much of the different elements are actually retained or goes back into the actual dust grain when it reforms. So here we plot the fraction of the different elements as the dust grain evaporates and cools back and becomes solid. So T-cool is when the dust grain starts to cool, and then T-solidus is the time scale where the dust grains become solid again. So the impact splash in this toy model actually easily retain most of the sodium, potassium, iron, and the different elements that we see in the chondrules. Of course, this is one particular model. It depends on the expansion speed and also what kind of environment that this impact splash happened in. The different lines, there are actually two different lines. One is a simplified radial transfer, and the other line is a full, complete radial transfer that includes the gas cooling and dust grain cooling process in 3 dimensions. So there are small differences, but the real take-home message is that the impact splash can actually reproduce most of the chondrules that we know of today. In reality, that goes into this calculation is the water fraction. Here I plot how much iron 3 plus and iron 2 plus during this cooling process and the formation of the dust grain. The different line, and also as a function of temperatures, the different line shows the different oxidation of these minerals. And it depends on the FO2 or the pressure of oxygen. Since water is the major carrier of oxygen, this whole process depends on how much water is in the disk during the formation of the chondrules. And in reality, also, since chondrules are, the sizes of the chondrules are between millimeter to centimeter, then the question is really, were there millimeter to centimeter dust grains in the early stages of star formation? And the solar system tells us there was. In order to answer these questions, we need dedicated ALMA observations of dust and gas and water vapor emission from various stages of star formation. In the infrared, we need to complement it with observations like the GWST, KEC, and future observations of ELT to understand all the different water features. The infrared tells you the emission from the inner regions and also the solid feature of the ice, which is primarily contains water. From the model side and simulations, we need to actually have a self-consistent astrochemical and geochemical model to really understand what's actually happening to the dust grains and molecules as the star and planet forms. So a short summary of the first section is that 1, solar system objects are indeed relics of the star and planet formation process. What it tells us that millimeter to centimeter dust grains were present when the young sun was born. And geochemical models are indeed a useful tool to study the early stages of planet formation process. So these whole studies can be connected to nanoscience, which looked at into the different isotopic composition of the different meteorites. We can actually look in detail how this isotopic composition compare to the molecular composition of protostars and also the different stages of the star formation sequence. And then the last thing is that we can test whether or not there was indeed a disk around the young star by looking at other systems. So this is what the next section is going to try to do. So protoplanetary disks is very complicated. Yes, disk wind outflows, the UV heated wall where most of the emission of the different molecules and hot gas is located. And then you have the warm molecular layer, and then you have freeze out or where the cold region in the disk is. So the disk itself is not that simple. So in the early days with the interferometer, we can try to look at the rotation of disks in various protostellar systems. Here with with the PDBI, we showed that there are gas motions are exclusive and recessive corresponding to rotation in various young stellar systems. Then we also have the 2D disk formation model that we can test this formation process against. So here we use a set of ordinary differential equations to dictate how the gas and dust parcels collapses from the large scale down to the disk. So here the colored diamonds correspond to the materials that are actually end up in the disk by the time the disk form. In this particular model, that's about 10 to the 5 years. The grayed out diamonds are the materials that goes into the star or ejected from the system in the outflow. So with the simple 2D disk formation model, we can trace how the dust grain evolves and also what kind of compositions they contain. In particular, we can also look at how efficient this process is depending on the initial conditions. So here I plot the disk formation efficiency as a function of rotation rate of the initial core. So in the initial dense core needs to rotate to actually forms a disk because it's angular momentum for this particular models. So not all, even with this simple models, not all parameters actually lead to disk formation. So there are some cases with this simple 2D disk model where actually no disk has formed. So in particular, this red color, when the initial dense core is very hot and very turbulent, then it could lead to a formation of very low mass disk or no disk at all, even though that the initial dense core is actually rotating very high, okay, very fast. The tools that we try to build up over the years is actually the really transfer tools that we have. We can connect the astrophysical model, so that's the physical model in terms of densities and temperature, with the adaptive refining in the inner regions to resolve the different velocity components and also resolve different excitation conditions of the different molecules. In the middle part, we combine astrochemistry and laboratory data to understand how those molecules are actually get excited in the inner regions at the different densities and temperatures, and also the physics of the radius transfer. And then finally, using all these tools, we can simulate the observables or something that we can test against the observations. And we can do this from near-infrared all the way to sub-millimeter. The most important point of this tool is that we focus on calculating the so-called contribution function. If we take the ray to the observer point, we can calculate how much the different ray elements contribute to that total flux. This is actually inputted, shown in this simple formula. Using the contribution functions, we can locate which parts of the disk or which part of the density actually contribute to the observed flux. Here's an example for a protoplanetary disk for COJ322 for a simple very massive disk. I think this is HD162296 for those people that works on this. Most of the emission, that's where in red, that's one, comes through this very small layers. If you don't have adaptive gridding, you don't resolve where this emission comes from. And most of the emission, in terms of 75%, only comes from this region. That's about 50 AU in size. So that's in sub-millimeter. Then we can do this for near-infrared for JWC and future observations in ELT that we just started doing to test, to predict what the ELT methods can actually do. So here's 3 micron emission line for HCN. This is a 50% flux that's coming from this region and also 75%. This is the line where the critical densities is. So we showed already that most of the emissions that we observe actually do not come from the regions that are actually where the densities hit critical densities. Then the line becomes awfully thick in this region, and also that's where the dust becomes awfully thick. So the 3 micron and 15 microns have different emitting regions, so they're sifted slightly and probes the different regions in terms of the photosphere of the disk. Using these tools in the past, we can actually calculate how much. Yes.
Sorry, so the last slide, which
Yes.
molecule are you talking about?
This is HCN.
18, okay.
Yeah, HCN R6 and HCN Q. For the protostars, we actually use this tool to really calculate how much the disk contribute into the total flux. If you actually has a beam pointing toward the protostars, then we can actually quantify how much emission that the disk contribute. Stage 0 is when the disk is very, very embedded, so this is the early stages of protostars. Most of the lines that we see, the disk contributes to less than 20%, so you will never see them at all, even with ALMA. This is what we predicted in 2013, so it's going to be very difficult. So we need to have the disk more evolved in order to actually contribute to more than 50% of the emission. And this is when the real disk that we can actually see. All right, so this is what the radius transfer tools are actually very important to do this. Then using the 2D disk model, we can compare the sizes that we measured from the observations. So the different lines are the different models of their initial site rotation speed and also their sun speed, what temperature that it starts collapsing. So these are all the different sources that you don't have to really know, but most of the things that we can reproduce most of the disk observations that we know of today with this simple 2D disk model. So this is all the sizes. The dots are all the different sizes of the disk that we see today, and the lines are the models. But of course, the disk formation process is not that simple. Simulations with magnetic fields show that it's very complicated to form the disk. So this is the part where the magnetic field actually removes a lot of the angular momentum and the disk do not form. And this particular model is when the disk forms. So we can take the simple radius transfer to look at what the dust emission would look like. They all look pretty much the same. So the red lines are the part that we can see, and all the color contours are actually the emission that we don't see at all. All right. So for H-on system here with the beam convolution of 0.5 arcseconds and 0.1 arcseconds, they also some kind of flattened structure that we all see in the dust continuum emission, and they do not correspond to real disk. Then we can use the line emission. So line emission is more or less Gaussian. So the size of this Gaussian corresponds to whether or not we have turbulence in the system, we have velocity field or thermal. So what kind of gas temperature that the emission comes from. So this is the equation of this Gaussian line emission. Then we can compare actually the line width of that emission with single dish data. So we have observations from 2 to 1 transition all the way to 9 to 8 transition with Harsono. So this is single dish data from the ground and Harsono observations for over 40 young protostellar systems. So the red and blues are the MHD models. So the red is the one that has efficient magnetic braking, so no disk formed, and the blue is when the disk is actually formed. And the green is a simple 2D model. So the 2 to 1 transitions and 3 to 2 that trace the large-scale molecular cloud, they tend to reproduce on the lower side. So there's not enough turbulence or not enough velocity field to reproduce most of the observations. If we zoom in to the high density region, so this is traced by the highest excitation, so 65, 10 to 9, and 9 to 8, then we actually look into the inner regions where the disk is forming. This emission actually really coming from the UV heated gas, so near the edges of the outflow cavity walls. The 2D models are better at reproducing the line width of the observed CO emission. Well, this actually indicates that the comparison to the image models is not that straightforward. It doesn't always correspond to one-to-one. And then we can actually construct the PV diagrams as what observers usually do. Is for the CT node 2-to-1 and 6-to-5. The models with the disk and no disk, they all look the same. This is what we've been trying to do and indicate that the PV diagrams alone is not enough to differentiate between the rotation or no rotation at all. So we need better tools, or actually then observe them and test them one by one. Thankfully, that's why we have AMA. So AMA has the sensitivity and spatial resolution to resolve the details of this process. So in 2018, we target this one protosolar system, the MC1A, where we see that the gas emission in green and blue, this 13CO and T18O, actually shows a hole, and the dust emission is in the middle, that's shown in red. With our ready transfer model, we can actually try to test whether the previous model that people have built are consistent with the new model, the new observations. So this is the blue shifted, and that's the red shifted emission. And if we take the previous observations and previous models that people have, this is what we predicted. In order to actually have a hole in the middle, we can either increase the disk mass up to 0.5 solar masses. So this is the mass of the actual central star. Because we know that if the disk has a similar mass of the protostellar system, it should be breaking or even has spiral arms. But we don't see any spiral arms or substructures in the disk at all. So the disk is very smooth without any substructures. The only solution is then to increase the grain size population to 1 millimeter. And we showed that the disk has to be populated with millimeter grains in the midplane and some of the smaller grains on the surface. So there's also settling in this very young disk, even at around 10 to the 5 years. So these observations indicate, that this hole in the middle that's present in the CO gas emission can only be reduced with millimeter-sized grain. This is an indirect way to reveal the presence of millimeter and centimeter dust grains and the settling of process of this dust during the planet formation process. And this is why the radiative transfer tools are very important. Now, the dust grains are not just dust, they have ices on top of them. And the dominant or the primary composition of these ices is water. So water forms first on the dust grains, and then CO and methanol, etc., forms in the outer edge. The protocell system has a cold envelope, the warm inner envelope. This is where it reaches 100 Kelvin, so these ices will evaporate, and then you can observe all these gases that once the ice evaporates from the dust grains. And then the disk itself has a water snowline, which is important for planet formation. In the early stages, the water snowline is actually further out than the later stage. However, since this is actually hidden in the midplane where the dust becomes awfully thick, you'll never see this at all. The best case is to actually look at the snowline in the inner regions where the emission can be actually seen. So we try to see whether or not the water vapor can be detected for this young protostellar system. We target a few water lines toward the young stellar system with the band 8 AMA and also with Platter de Beer. So this is highly excited water line, and this is the lower excited water line. The reason being is that for the same column densities, the bandwidth waterline should be stronger, while this line that is being observed at Noema should be weaker. But then this has a higher optical depth effect, and this has lower. So we try to do both in order to see whether we can detect the water. But we didn't detect any water emission at all. So the water vapor is missing from this disk-forming systems. One way to conceal a lot of the water is that large grains form very quickly, and all these large grains are actually water-rich. So we can plot the abundance ratios of the water. This is what we expect, and this is class 0. We do detect some water for earlier systems, but once the system has an actual protoplanetary disk that is actually forming, water is missing. In order to deplete all this water very quickly in the star planet formation process, you grow the dust grains very quickly. So this cannot be confused because water emission, water vapor has 3 different origins. One is the surface layer on the envelope. That's about hot water. That's seen with Spitzer. And then the warmer water also seen with Spitzer and from the ground with VLT. But the planet formation water that corresponds to what kind of water goes into the planet are actually in the middle. This we don't see at all. So that's basically what the water story is telling us. These results are really consistent with star formation models? This is still to be determined. So we need, again, dedicated water survey and also dedicated models that include dust growth and looking how the molecules and different molecular composition evolve as the dust grows during the disk formation process. So that's what the summary 2 is, that the spatially resolved observations are needed to really look at detail of the disk formation process, and finally dust growth is actually seen directly and indirectly during the early stages of star planet formation. And finally, the last slide section is on the gas and dust composition. So this process, from the collapse onto the formation of planets, we can trace the different molecules that's in the ice and gas as it evolves. We use the 2D disk model to look at the ice composition for the models that actually form very small disks and very large disks, and they do affect the ice composition. If you form the disk very early, you actually have more complex organics that is actually beneficial to form more complex species. Then, if you look at a burst system, so during the horizontal burst, you can actually look at the molecular lines and trace what kind of composition of the ice is, because during the burst, that's when the ice composition gets released. So then we can do this for HDO and H280. This is HDO fraction and H2O for the different regions of comets and protostars in cluster and isolated. What we did show that the isolated regions have different deuterated fraction with respect to the comets and also cluster protostar system. And this is where the Earth deuterated fraction is. So it seems likely that the deuterated, the time scale of the star formation actually can be traced with the HDO and H2O. In the cluster system, the protostar formation is quick, while in the isolated case it's longer. Then you have more deuteration in this process. And finally, the ice composition actually evolves as the materials goes into the disk. In the earlier phases, you see ice features of amorphous water and ammonia, and also some large grains in the wings. And it goes into the center, you have the water becomes to crystallize because of the heating process as it goes close to the protostar. With TAC and RTF, we try to look at the process of water and complex organics molecules toward background stars and also the earliest stages of star formation. We see some evidence of methanol and some ammonia and water feature here, but not all of the directions actually contain methanol. So only a few detections so far, and this process is still ongoing. Then we can connect how much material is actually in the envelope with the materials in the disk itself. So this is the same system, TMC1A, where we look at the CO, HCN, and SO. So HCN is somewhere near the envelope, and then the disk is traced by the grayed out background. The question what we want to answer is that whether the molecular abundance of the envelope is the same as the disk. Since we now know what the disk is, we can compare the exact molecular composition of the disk and the envelope. This is what we did. This TMC1A envelope, this is in yellow circle, and the disk is in this blue out, grayed out square. What we show is that the envelope fraction for the different molecules are very similar to the disk fraction. So the compositions are the same. So that means the disk is inheriting the molecular composition or all the chemical species that was formed during the star formation process. So everything is inherited. Then we can compare the disk of this one particular TMC1A that's very young to class 2 that's more evolved. So this is comparing the blue one with the purple squares and rectangles. So they are very consistent except for HCN and CO, which we can actually compare with comets. So it seems that some of the materials that inherited by the young disk is actually conserved throughout the evolution of the disk. So all these processes indicate that a lot of the planet-forming materials are actually inherited during the earlier stages of star and planet formation. And finally, this is where the comets are located, and that's interstellar comets. There are some differences here. So HCN and water is actually the molecules that we want to observe. We don't have that many detections, and yet they are actually important to show the disk formation process and its evolution during the planet formation. So we need to target these molecules more. So the way forward is to bring physics, astrochemistry, and also geochemical models together. By doing this stuff consistently, we can test with observations in the submillimeter and infrared. As a part of the JWST ERS program, that's the early release science, where we target a lot of the ICES toward different stages of star and planet formation, we can actually test then what the ice composition tell us with the submillimeter data and whether or not the gas composition are similar to the ice measurements. Then eventually, by putting this all together, we can try to understand how much water in this evolution will be conserved by different planets in the different disk evolution processes. So this is what San Raymond did, looking at how much water goes into the different planets with different initial conditions of the disk. So in this talk, I showed that solar system's objects actually has crucial information of the star and planet formation. Geochemical models are important, and it still needs to be incorporated into the star and planet formation studies. So planet formation starts in the early stages of star formation, and finally, the formation of the disks actually affect the chemical composition of the planet forming disk. So whatever goes in at the earliest stages of the disk formation is what is left. That is what the gas and dust that will be going into the planet. So the ongoing directions that I'm taking right now is that I'm developing those physical models that's mostly in 2D and will be in 3D that will include disk wind and magnetic field, etc., and also incorporating the geochemistry. In the infrared, I'm part of the projects to look at for ICES into the complex organics by providing ready differential models, and also with VLT, Muse, to look at the disk wind processes and the composition in the inner regions where rocky planets are forming. So, and then in some limiter, we are submitting we're doing water surveys and also astrochemistry of the infalling gas. We have JCMT with transients, also Nobuyama telescopes, observations that we've been doing for the past few years to collect astrochemical data for singles and multiples to understand how multiplicity actually affects the chemical composition. So these are the feature projects that I will try to bring as in ASIAA. So we'll try to combine the physics of star and planet formation with astrochemistry and geochemistry to look at the impact onto the formation of minerals and chondrules, and also the composition of meteorites. I'll develop the self-consistent theoretical studies that can be tested against infrared to submillimeter, but in the models itself, actually, we include X-rays, heatings in the gas, and how that actually affect the molecular composition. So the current and upcoming experiments and observations can really bring astrochemistry, star formation physics, and geochemistry that goes into the meteorites really together. So hopefully in the next few decades, we can try to build a self-consistent picture of star and planet formation, and then include that dwells into understanding the origin of the solar system. With that, thank you.
So we have 15 minutes for Q&A. So if you have questions, feel free to ask.
Yeah, thank you for very nice talk. And actually, I have several questions, but I can ask you just one this time. Okay, so yeah, regarding the so studies of disk formation. So I don't clearly understand what are the key questions of that topic, and then the next is you try to understand so using relative transfer and so on, and so how you try to tackle those questions, and then so if I understand it correctly, so I mean your work is not so things are not yet conclusive, and how could it be improved in the future? For example, new missions, new approach, and why they would work much better.
So is that the one question? Or so the disk formation process is still not fully understood, since we know what the end product is and we know the composition in the beginning. So in terms of this slide, we pretty much know the compositions here and the compositions here.
Yeah, in the beginning, the composition is
Yes.
Similar to molecular plasma.
Yes.
So
Yeah.
molecular plasma.
So now we know a lot of studies in the later stages, and we have a lot of studies in the pre-start course. We still do not understand of how those materials get incorporated during the disk formation process. So the question is, that corresponds to whether the disk forms very early or late. Recent numerical studies shows that magnetic braking can really delay the disk formation process, and how that actually affects the eventual outcomes of the structure and composition of the disk once it reaches this stage is still unknown. By looking at the molecular lines, what we did with ALMA and Plata de Buer, we can actually compare this with our own models, and they do look self-consistent. So the question is whether or not those observations actually tracing the materials that are being simulated in MHD simulations. So where are they? We know that magnetic fields are important, but it seems that the emission lines that we detect are not tracing those regions at all. If they are actually being reproduced by simple 2D models, then we are only tracing the hydrodynamic components. And we still don't know how those materials are being delivered from the early stages to the later stage.
Okay, thanks.
Okay, more questions?
for HDO or D2O.
Yes.
But then, how much you know about those kind of isotope ratio or deuterium ratio? It really depends on those kind of understanding, right?
Yeah. So for at the moment, in terms of isotopic composition, 17O and 18O, that's really set during the AGB phase, and it seems to be fairly consistent for various star-forming regions. So we can adopt the galactic 17O and 18O and use that, and it seems to be okay. So the question is whether the HDO story and D2O story. The HDO and D2O, I didn't present the D2O because that's a different topic by itself. It's actually being formed, depends on the star formation timescale. If the star formation is delayed and the materials and the dust grains sits in the colder region, it gets deteriorated more. In the cluster system, when the star formation is quick, so it's triggered somehow, then the star formation process is very short, so you have less deterioration. So in terms of HDO water story, what we really need is HDO and D2O story. But in order to do this, since HDO and HDO and D2O are very, very weak, we need to look at the H218O first. Then H218O is the stronger the water line. Once we know where H218O is, we can scale the H218O to HDO, depending on whether the system is isolated or clustered.
But for the for the
Yeah.
ATO, the isotope ratio, is that different from the inner part of the galaxy and outer part, which is different?
They are slightly different, but for most of the systems that we can do is nearby. So there are no large gradients in terms of 17 and 18O. Since 18O is actually coming from this really inner region, we really need to target systems that are very nearby that we can actually resolve within 20 to 50 AU. Once the beam is larger than about 100 AU, we won't detect any H218O emission at all. What we predicted, we need 25 hours of ALMA time to detect H218O for one object and one line. So if we can do it in the longer baselines, then we can actually try to see this in the shorter time integration.
Okay, we have one question from Nagoshi. Nagoshi, please. Hello?
Yes, sorry, I didn't confuse them.
Okay.
Yeah, thank you, good talk, Daniel. So I have a question about the disk formation, which you discussed earlier. So you are talking about the magnetic braking would be one important factor which can control the disk formation. But I have not, well, probably I'm not studied well myself, but I haven't really seen the particular sort of evidence in which magnetic braking is really controlled, except for some theory. Observationally, there is no particular evidence. So if you have any comment, I want to hear that. And at the same time, angular momentum is of course not supposed to play the important role for the disk formation. So then another question is, how angular momentum or core rotation will be controlled or determined, which has some impact on the disk formation. I would like to share if we have any comment on that.
I repeat the question. Nagoshi asked about Daniel's comment about the magnetic braking on disk formation. And the second one is about any of the observations to test the angular momentum, what the impact of angular momentum on disk formation.
So for the first part, the magnetic braking, so far the observations that we have actually shows that there is no magnetic braking. So at least there's actually minimum. So that's what it is. So the question is whether or not those emissions are actually the ones that we should target in order to see how magnetic field affect the disk formation process. So there are a few molecular lines that are very weak, that's mostly controlled, that's connected with the magnetic field, that could be potential to trace how the magnetic field structure looks like during the disk formation process. But a lot of this chemistry is still it's affected by the UV and X-ray and the feedback of the polar stars, and that's still not well understood at all. So that's the first part, that we still need to have self-consistent models with the MHD simulations, what they actually predict in terms of molecular compositions and where those emissions come from. Most of the MHD simulations actually only set 10 to 100,000 years. It's not actually efficient to compare with observation 1-to-1. Well, the 2D models can go from 1 million years before the star formation up to 1 million years after the protostellar system, but it's simplified. So we need to work further in the MHD models to see whether or not we can simulate something that can be compared with observations directly. For the second one, this is coming back to early models, I think simulations by Sammy Dip in 2010, where they simulate what the molecular emissions from the molecular clouds as it rotates and falls and forms protostars. And they show that the angular momentum that is predicted from the simulated observables can be off by orders of magnitude than observations directly. So we didn't try to do that at all in this model, because we know that the measured angular momentum is not exactly the same as the observed angular momentum. So you're always off, and sometimes by up to 10 orders of magnitude, a factor of 10. So that's what we know as of this moment. But certainly we can try to test the simulations that we have now and see whether we can, what is the best way to extract back that angular momentum that is in the theoretical models itself.
Okay, good. So we have time for one more question. So I have one for you. So you mentioned to determine a disk using Keplerian calculation is not sufficient. You need actually 2D radiated transfer to determine the disk size. Have you compared how much difference between these two methods? Literature.
I don't have the slides. Okay, I might not have the slides. Yes, we did. It's between a factor of 2 smaller up to a factor of 5 larger. So that's what we see from comparing the different simulations and the 2D models. So we took the emission models and we tried to extract back what the observers tend to do, and we're off by a factor of 2 smaller up to a factor of 5, depending on the combination, how the models are being rotated. The best way to solve this is to use CO and DCN and DCO plus. So you look at the hot gas and also the cold gas, where it's coming from. And this seems to be the better way to constrain the size of the disk when it's actually forming.
Okay, so that's good to know. Thank you. So I think time is up. If you have more questions, please do it in a one-to-one discussion. Okay, let's thank Danielle.